Hi, my name is Steve Ulrich. I'm with Juniper Networks. Get right into it. The intent behind this talk is to really encourage us to start having practical operations-oriented discussions around segment routing. I think we've all, for the last 6 years, gone through a number of the breathless marketing presentation that extol the wonders and virtues of segment routing, how it's going to make our lives easier, how it's going to dramatically reduce the costs and improve the efficiencies of everything. This conversation is a little bit different. This is a talk about some of the things that we don't talk about when we talk about segment routing typically, when we're waxing poetic about what segment routing is going to do for us. I want to point out I'm not going to be bashing segment routing. I think segment routing is an incredibly important technology for us to move things forward. And some of the things that we're talking about here, nothing's intractable. This is just a lot of hard work, and we're going to have to start talking about this. We're still working through a lot of the issues, and I'm just going to surface some of the issues in the discussion today. I'm not posing solutions for any of these necessarily. We point out some of the relative trade-offs for the technologies that are under active development and some of the practical deployment considerations that we're grappling with as we start forging forward with segment routing. It's going to take some time. There's going to be some bruising. There's probably going to be some scarring. And for those of you who are anxious to get to the Peering-Boff or break for beer, if you're looking to simply replace LDP, you can probably skip straight to the end. The folks I spend most of my time with are interested in flinging their packets in a specific direction and doing something fairly stringent with the traffic and steering around the network. So if you're looking to replace LDP, most of this probably doesn't apply to you. You might still find it interesting. So a brief overview of what I'm going to be talking about here. I'll do like a 3-slide review of segment routing. I'm going to talk about kind of the obvious things that cause a knee-jerk reaction or gag reflex when we talk about segment routing. Label management, RSVP and SR coexistence. Some of the less obvious things when we're talking about segment routing, the care and feeding of the controllers, the ubiquitous controller that will solve a lot of our problems and that we're going to be increasingly dependent upon in an SRTE environment. A little bit of discussion around SRTE protocols. There's a number of them to choose from. What are the relative merits of those? A little bit of discussion around traffic protection and the state of things there, and effectively a call to action for more discussion around what's going on with segment routing from a practical deployment perspective. So, segment routing types and label spaces, and I'll use the term segment, SID, interchangeably. Apologies in advance for that. There's effectively 4 kinds of segments or SIDs that I'm going to talk about today. One is the adjacency SID. That's the interface-specific label. It's what we typically see in our IGP today. The next one is the prefix SID. You might hear me interchangeably refer to that as a node SID. That represents the least cost path to a particular prefix in the network. Node SIDs are a special kind of prefix SID. They're commonly bound to a loopback interface. These have domain-wide significance. So this is kind of you can think of it as a consistent pointer or a consistent destination inside the network that everybody has the ability to forward traffic to at the data plane. 2 less commonly discussed but important SID types here. Anycast SIDs, where it's an anycast announcement of the same label for a prefix binding. This represents the IGP least cost path to a non-unique announcement in the network. And a binding SID. And I'm kind of doing a binding SID a little bit of a disservice by saying it represents a tunnel. Binding SID is a very useful tool in segment routing from a traffic engineering perspective, in that it allows us to define, it may be a number of SIDs, it may be a SID list, it may be a number of SID lists in order to define a path that we're going to bind traffic to. You can think of it as kind of search and replace in the path for segment routed traffic. A few comments about segment ID space. SIDs are not labels. They practically manifest themselves in the network as labels, but they're encoded or carried in labels. A SID, especially in the prefix SID domain, is effectively the announcement of a base or an index, a base or an IGB, a label range, and an index into that label range. Domain-wide SIDs are flooded into the IGP, so everybody understands what they are. They're allocated very much like like you'd allocate 1918 address space today. This announcement of a block plus an index, the block itself is here referred to as the sRGB for the segment routing global block. The global label that everybody's interested in the network is effectively the sRGB base value plus the index for that node. I'll do a quick run through two forwarding scenarios. Across the bottom, going from router 4 to router 7 on the right, we have a label stack here on the left for presentation to router 4. On each one of these segments, we're going to pop and forward. So router 4 is presented with label for 45. It pops that, forwards label stack with 56 and 67 out the interface associated with label 45. It gets to router 5, pops the label, forwards 67. 67 is associated with the penultimate hop for router 7. We pop that and we forward the raw IP frame out to router 7. In the top portion of this topology, we'll demonstrate a little bit of the expansion of the sRGB and index behavior. The index is, or the base is indicated here in the square brackets. If you look at router 1 to router 7, the shortest cost path to that is via router 2. The index for router 7 is 7, but router 2 expects to receive a label within its particular base and is receiving a label for 507. The process is repeated at router 3. Penultimate hop popping takes place, and we present a raw IP packet to router 7. A little bit about anycast SIDs and binding SIDs. The diagrams at the bottom are largely for illustration purposes. Anycast SIDs, again, have a domain-wide significance. This is a set of nodes that use a non-uniquely announced prefix. The forwarding choice is made via the IGP best cost, least cost path to that destination. ECMP may be used for forwarding. We commonly use anycast SIDs to represent a geographically close set of nodes. You might think of it as core routers for a particular metro. This also enables us to utilize load balancing, and it provides redundancy in the network. Binding SIDs, this search and replace for stuff at the data plane. These have node local significance. They're bound to other SR paths. This may be multiple segment lists or SID lists. From a data plane perspective, we pop that label and we forward by imposing the forwarding stack for the path that we want to define. We may actually specify multiple paths and do things like weighted ECMP across for traffic presenting with that particular binding SID. So I'll segue to the obvious stuff, the stuff that people pay attention to when they start to think about segment routing deployment. From a global label space perspective, this is our prefix SIDs, our node SIDs, our anycast SIDs. This is pretty well baked out. Major routing implementations have demonstrated pretty good interoperability. There's a little bit of attention to the deployment of anycast SIDs that you probably want to be careful about. It's strongly recommended that the sRGB for nodes which are announcing anycast SIDs have an identical sRGB value or sRGB range. The drafts are pretty clear about this point. The other thing that is important for the controller and for those who are deploying with anycast SIDs is that labels which resolve underneath that top anycast SID that you're forwarding to must be resolvable by downstream nodes. So you kind of have to pre-bake that label stack from a controller perspective with an understanding as to what the subsequent forwarding operations and the perspective of the network is for subsequently forwarded traffic. As we've gone about kind of demonstrating interoperability from an anycast SID perspective, the conflict resolution behavior has been pretty well teased out. There's still some opportunity for misconfiguration and blackholing of traffic. For example, if I have a node which is announcing the anycast prefix but is not announcing a corresponding anycast SID, you may see blackholing for traffic. The behavior is very similar to what you might see with LDP if you didn't turn MPLS and LDP on a particular interface. It can be really difficult to kind of troubleshoot that one. At the root of it all, SPF is done commonly against what the IGP's address family is, and the associated SID resolution is kind of a byproduct of that. So a little bit of care needs to be exercised in terms of ensuring that you consistently deploy anycast SIDs with this consistency of binding and operation. A slight segue around local label space. Different vendors have had different implementation and deployment considerations around how they manage their label space. Behavior of the sRGB is pretty well baked across implementations, and there's good reason for that. Devices which have very small label space, or the hardware is limited in terms of its label processing capability, might require special attention in terms of in terms of label allocation. But some implementations use labels locally on the device for other things, or there might be kind of additional services that go along with that. Examples of this would be service-specific labels that are used for things like egress peering engineering, where you might be doing an interface lookup and forwarding operation over a specific interface to override the forwarding, the native IP forwarding behavior, or if you're doing things like associating labels with individual member links on a link aggregation bundle, and you want to be able to verify the path for that. If you bake a label stack in order to exercise all of those member links, you'll want to do that with an awareness as to what the label allocation is for those deployments. This is the one that seems to come up most commonly when folks are talking about segment routing, label stack size. I'm carrying a ton of overhead in order to forward a TCP ACK. One of the seductive things about segment routing is it provides for very granular traffic engineering. The controller does the imposition of a label stack. You can mix and match labels in the stack in order to achieve certain objectives. But you can get, you can define the path on a per link basis all the way across the network, just like you can with RSVP today. And this sounds great, but it entails a number of additional considerations. And the first one that leaps to mind here is hardware encapsulation capabilities. Some hardware, candidly, is just severely constrained in terms of the numbers that it can, number of labels that it can impose on a single pass. This includes some pretty popular chipsets. Some hardware is definable on this with software upgrades. Some it's just baked into the forwarding pipeline. Now, if you control one end of the connection with virtual host or vSwitch capability, you can potentially offload some of this NCAP with your host stack. If you're a transit or a network provider, you'll want to pay particular attention to the capabilities that you have on network ingress if you need to do fine-grained traffic engineering. So if you need to do that per interface level of traffic engineering, pay careful attention to what the hardware is capable of doing. The plot thickens. You doubly want to make sure that you understand what the hardware capabilities are, because it's not just label imposition that you have to be aware of. You have to take into consideration the fact that some hardware might have undeterministic behavior when it experiences very deep label stacks and it doesn't see the bottom of stack bit. So will all of the transit links in your network support forwarding deep label stacks? Will all of the line cards in a system do that? Will the load balancing behavior be consistent if you have, say, a new generation of hardware which is capable of forwarding on these deep label stacks, but it load balances across links which don't necessarily share that same capability? For nodes that do support forwarding on deep label stacks, and this isn't a concern, do you have access to enough entropy sources? Are you peeking under the hood of that label stack in order to assure that you get the load balancing that you're after on the on lag members? And are you potentially obscuring critical entropy sources for forwarding and ensuring that you get load balancing? Now, some of you might be saying, hey, this is no big deal. I'm going to use anycast SIDs and prefix SIDs. I'll define my paths. I just want to fling traffic in that direction. And I'm going to have this small, thin label stack, and it's not going to be a concern. We're going to come back to that because it actually becomes a bit of a nuanced consideration when we start talking about contributing sources of flows and traffic in the network. I'll shift gears a little bit here. A lot of folks that we're talking to are, who want to do something with segment routing from a traffic engineering perspective already has RSVP deployed. And there's this conversation that we persistently have around RSVP and SR coexistence. And at the end of the day, the tacit assumption, or dominance assumption rather, is that you want to move from RSVP to segment routing. That might be because there's a range of kind of architectural shifts that you're going to go down. Maybe you're focused on horizontal scalability. You want to take advantage of the fact that segment routing provides for leveraging wide ECMP inside the network. But if there's this long-term need to run RSVP and SR in the network at the same time, it's probably in your best interest to look at introducing a controller to manage traffic across both the SR and the RSVP domains as quickly as possible. This is particularly important for folks who are durably managing things like point-to-multipoint TE in their network for a long time and have point-to-multipoint considerations from a service delivery perspective. So the real gotcha with SR and RSVP coexistence is this problem of dark bandwidth. Whenever we're just injecting SR traffic into the same domain as RSVP TE LSPs, we run the risk of robbing capacity from the RSVP space. This is a generic problem associated with with the management of dark bandwidth pools. There's a draft here which is currently in working group last call, which provides a really nice breakdown and discussion of the migration considerations. And I've candidly ripped off some of the content from that draft to break out some of this discussion. So the draft and the conversations we're having here kind of break this out into a number of different considerations. We looked at a few things here. One is static bandwidth partitioning. On each link, I'll just assign so much bandwidth to each domain, and SR traffic is admitted into the network in order to satisfy those requirements. RSVP does its thing. The problem here is that we haven't really solved the problem of dark bandwidth. We're stranding capacity which might be left behind by one protocol versus another. Another mode of operation is to just introduce centralized capacity management, a controller into the domain to facilitate introduction and management across both domains. But the rub here is that if your long-term goal here is to move to SR, you're introducing a controller for something that you're effectively going to throw away with the management of the RSVP traffic. Another approach that folks have discussed is flooding the SR utilization into the IGP. And then what we could do is we could modify the decision process on RSVP TE head ends, change the CSPF algorithms to accommodate for this. This carries with it all the associated downside of reworking RSVP and bumping a bunch of stuff that works, and there's not a whole lot of gain to be had there. Another mode of operation might be running SR directly over RSVP. So you effectively resolve SR destinations over IGP shortcuts in the RSVP TE domain, but then you have this problem of how do I back it out? And you don't want to have a circular dependency here. What we've more or less settled on and are starting to see some exploration of deployment with is reflecting the SR traffic utilization into the IGP's max reservable bandwidth here. At first blush, this looks like the option I outlined on the previous slide, but in this case what we're doing is we're measuring the overall SR traffic on the TE interfaces and reducing the amount of available bandwidth that's there for RSVP. We don't have to change anything in terms of the existing RSVP TE machinery. This does make some assumption that the auto bandwidth machinery is in operation in the network already, and this has the added perk of allowing you to introduce an SR-only controller into the network. The algorithm out here that is outlined on the right-hand side, we retrieve the SR stats, we calculate a smooth average here, we flood that into the max reservable bandwidth value. There's some discussion that could be had around what priority do we flood that into the network. But the punchline is the RSVP-TE head-end nodes can then adjust their LSP accordingly, and traffic effectively starts to move away from where we're loading the links with SR traffic, and we're pushing RSVP incrementally to just the RSVP-only enabled links and domains. From here, I'll shift to some of the less obvious stuff that becomes apparent when you start to dig into and under the hood of actual SR deployment. I'll start with a little bit of a segue here around controllers, and they're incredibly important but often underrepresented companion, the collector. At a high level, the controller slurps the LSDB from the network. It gets a picture of the topology. You can do that any number of ways: a passive IGP peering relationship with the existing network, BGPLS, reflecting those attributes out into the network, or you can get this out using streaming telemetry. The controller takes into consideration the network state, the utilization. It gets that from the collector. It kind of munges this all together with an understanding of what the traffic demands are, and it presumably understands what the hardware capabilities are and what the projected loads are going to be, and then it pushes down a segment list to the ingress to put traffic onto the network. And from there, we're going to kind of talk about some of the options for pushing that information into the head end and what the relative merits of some of those approaches are. At a high level, there's a lot to love about centralized path computation. It has the best view of what the available resources are in the network. There's really no other place in the network where we have this kind of visibility. And now we can start to kind of realize the actual potential of some of the software-defined capabilities in the WAN. This does carry with it some attendant considerations. You have to buy a collector, or you have to develop your collector or your controller. Well, you have to do both. This carries with it staffing, some code dependencies in terms of what the capabilities are from a control plane perspective and from a controller perspective. And with the introduction of a controller, you have new availability considerations and new concerns around what is the policy that's being pushed into the network. So the thing is, with segment routing, all of the traffic engineering is controller driven. There are some new developments that are taking place right now in order to provide what is effectively, I call it RSVP without soft state, where we provide dynamic policies which take into consideration things like link affinity, SRLGs. But by and large, folks are looking at using controllers in order to push down the policy and the admission for SR traffic. And one of the hottest area of conversations when you talk to either an RSVP developer or an SR controller developer is label stack compression. And that holds true whether you are talking about doing this on box with these dynamic policies, or whether you're talking about doing this off box at the controller. Which brings us to the care and feeding of our controllers. The care and feeding of our controllers requires a lot of telemetry information. The auto bandwidth and the machinery that we had previously in the RSVP domain has to move somewhere. So a controller needs to have visibility into the traffic loads. It's got to understand what the situation is and be able to proactively move traffic loads or deal with failures in the network. This implies a lot more aggressive instrumentation than we've historically seen inside of today's networks. The previous discussion around streaming telemetry is a critical component in terms of actually enabling us to do segment routing deployments with visibility into what the actual network utilization looks like. So probably the pre-step for all of this is to really look at reworking your instrumentation to utilize streaming telemetry. And as much as I thought I'd be kidding about it, the practical reality is we are talking about actually getting access to per label traffic statistics. The reason for that being that folks want to have small label stacks, and they want to understand what actually is the contributing flow for whatever traffic is coming into the network element. So we need to talk about stats. And given that we need stats, what does the hardware actually enable us to do from a stats perspective? Now, if you had everything, you'd have access to per interface, per direction, per label, per traffic class stats. And then you'd want all the same for whatever you're pushing down in terms of policy into the device. Unfortunately, the reality is far uglier. Outside of fib capacity and ACL space, counters are the most precious resource on modern ASICs. And so you're going to get some subset of that list. And it's probably going to be a disappointing subset. The other thing is getting the stats off the device and cycling through all of the per interface, per label stats that are on the device is going to require likely new collection infrastructure. So you want to revisit the previous presentation and see about looking at collector options. Now, if you do get some useful subset of stats information, what does a label counter actually get you? Anycast prefix SIDs, they're actually a great place to hide traffic. All sorts of traffic that's destined for a particular metro is actually hiding underneath that. You're actually going to have to look and see what's hiding underneath that label. If you're looking at SRTE policy counters, you're going to have to look at how many policies actually collapse to a common anycast or prefix SID at various midpoints in the network. And you're probably only going to get this in one direction. This is going to require a lot of planning and management on where you put your traffic sources and sinks. And at the end of the day, I'd really like to encourage you to look at your IPFix and SFlow collection infrastructure and look at that to provide the visibility underneath those top label stats and divorce yourself from classic forwarding prefix and associated router metadata in order to get at that information. I'll quickly segue to SRTE traffic engineering protocols. There's three that I'm going to discuss here. BGP SRTE, this is a very active draft. There's a lot of development taking place in this space here. This is very useful in ECMP dense environments. It doesn't specify an interface. There's no interface tunnel TE or named LSP. Instead, you want to think of this as policy and rules for steering. This allows you to specify a segment list or a range of segment lists, which would be weighted ECMP forwarded from that device. Which brings the question of new considerations around data plane programming and validation. This is BGP. I kind of have to trust that you did what I sent you to, what I told you to do. Do you know that the node actually accepted the list of segment lists you sent it? Do you know what got tangled up in policy logic? The answer is you don't. You have to go and interrogate the device in order to do that. You want to be able to do that in a scalable manner. So you'll want telemetry for that. Did you get to specify a protect or a bypass path? No. And if you really need to specify a bypass or a protect path with some awareness as to what the capacity and the utilization will be on that, this might not be the tool that you're looking for. Next is PSEP. PSEP has been extended to provide for segment routing LSP configuration. It has a range of delegation and management models that are pretty slick. It does retain a bit of an RSVP-ish worldview. It's capable of signaling the paths, doing nifty things like flow mapping, and using for this for something other than IGP shortcuts is still a work in progress. Actual definition of a protect path is work that's underway. There is a draft that discusses protect path placement. It's due for a refresh. Now, one really interesting thing about doing this is that you actually get fighting chance at some sort of a contract with a node. Instead of the trust but verify mode of BGP operation or spray and pray, you can actually understand what the node is capable of doing it based on the actual capabilities that you negotiate with the PSEP, with the PCE at that ingress node. A more recent development that we've been talking to folks about is actual RPC-based path placement. A number of operators are looking to leverage the RIB APIs that every vendor has been popping up with lately. Juniper's got PRPD, Arista has EOS, I believe Cisco has a service layer. There's something called GRIBI, or the Google RIB interface from the OpenConfig folks. All of these provide a mechanism to define label stacks and paths, and they provide mechanisms to associate RIB entries with these paths. This enables you to build an agent or to do something novel in terms of actually doing controller selection or actually creating a bypass path that is under your control. The other thing that it does is it freshens and modernizes the toolkit for folks from a development perspective. So instead of using arcane protocols in order to do this, you can start to take advantage of the more modern toolkits and SDKs that vendors are providing here. The flip side here is it does require internal development expertise. You are leveraging a vendor's specific interfaces and APIs in order to get the job done here. And this carries with it all the baggage associated with testing and verifying those APIs that you're getting from the vendors on subsequent code releases and new deployment and packaging considerations. Finally, I'll leave you with a bit of discussion around SRTE traffic protection. The old ad was, it's 1 a.m., do you know where your children are? Well, it's 1 a.m., do you know what your protect path is? Chances are you probably didn't get to specify it. The knee-jerk reaction in the SR space is to talk about TI-LFA, and there's, truth be told, a lot to like about TI-LFA. There's no midpoint state. The fact that it comes up with a true post-convergence path that's optimal and has no microloops is huge. But the practical reality is it's pretty computationally intensive, particularly if you have things like SRLGs. It may very well require label stack compression to stay within whatever your protection and cap capabilities are. And so all of that conversation that we had previously around instrumenting the traffic, the hardware capabilities from a transit path or from a label ingress and imposition perspective holds true for what is now traffic protection that is largely outside of your control. So from a practical deployment perspective, protect path placement, let's just put it under the domain of an area of active development. And if you're looking to deploy and have a strong need for specified protect path placement or a need to garner that in advance, you'll want to start talking with your vendors and the standards bodies about what we need to be doing here. So in conclusion, I'm out of time here. TE with SR, it didn't really get easier, it just got different. There's a lot of work that remains to be done in terms of operationalizing this. The data plane simplification, the elimination of soft state, this is hugely useful for us going forward as we look to build networks differently. But we're going to have to build complementary toolkit and infrastructure in order to account for this. And in many cases, we're probably going to have to roll our own solutions. So in the meantime, there's no silver bullets here. You can expect an interesting workplace as we work through the implementation considerations here. And in the future NANOG, I really hope to listen to some presentations from operators who are really digging into the weeds on some of these problems and putting forth the solutions or the operational experiences that they've had. And with that, are there any questions, I guess?
It's not a question, Steve. It's just a comment. So I'm Rob Shakir. I co-chair the Spring Working Group in the ITF. This is somewhere we're really trying to focus the working group on. So bringing the realities of the things that we can't deploy and the things that are difficult to deploy. Please bring them to the working group. We're listening. We'd love to work on them. This is some IETF NANOG outreach.
Okay then, thank you.